Hello everyone, welcome to the course on electromagnetic theory and interference. In this session, we are going to see the mode propagation in rectangular waveguide and followed by transverse magnetic mode. We already discussed about the wave equations in rectangular waveguide in the previous session. Now let us see the modes of propagation in rectangular waveguide. So we have seen from the 11th and 12th equation, that is Ez and Hz. Similarly, 12.15, this equation will give me Ex, Ey, Hx, Xy. From these actually six wave equations we have found, we can notice that field patterns or configurations, field configurations can come in different types. Each of these distinct field patterns only we term as mode. Okay, mode in rectangular waveguide is nothing but distinct field patterns. The wave equations, okay, will give us distinct field patterns. So there are four different mode categories are existing. Okay, the first one is TEM mode, that is called transverse electromagnetic mode, where the electric field and magnetic field both are transverse to the direction of wave propagation. That means we know that the wave is propagating along the Z direction, and rectangular waveguide is the broader dimension is placed along the X, as we can see in this picture, and narrow dimension B is positioned in y-axis. So the wave is going to travel in Z direction. So in that case, the electric field and magnetic field component along the wave direction is actually zero in TEM mode. So if we substitute EZS and HZS as zero, okay, we know that all the terms get vanished in equation 12.15 that we can see in this slide, because all the components Ex, Ey, Hx, Hy, everything is dependent on the Ez and Hz. If both are zero, all the field components are going to be zero, and that won't exist in rectangular waveguide. So rectangular waveguide cannot support TEM mode. The next mode is transverse electric mode, where Ez is zero. That means the component of electric field along the wave propagation is zero, but magnetic field will be present along the wave direction. Other components will be there as it is along the X and Y direction. And coming to the transverse magnetic mode, it is just opposite. That is the magnetic field along the direction of wave propagation will not be zero. So will be zero. That is Hz is equal to zero, whereas electric field along the wave direction, that is along the Ez, will be present, and remaining components will be there as it is. And the last case is nothing but if both are not equal to zero. If both the electric and magnetic field along the wave direction is not equal to zero, that is called hybrid mode. Okay, that in this case, neither electric nor magnetic field is transverse to the direction of wave propagation. Okay, actually, we are going to see only these two modes, transverse electric and transverse magnetic mode. The first and fourth mode, TEM as well as hybrid mode, does not exist in the waveguide. Now let us see about the transverse magnetic mode in the upcoming slides. So as we know, in transverse magnetic mode, the magnetic field along the wave direction is zero, but electric field component will be present. Okay, and we know that if we set Hz is equal to zero, okay, out of the six wave equation, we can find the rest of five, Ex, Ey, Ez, we have already found in the previous session. Hx, Hy also we can find. How we can find? By using the standard equation that we already found in the previous session, along with the 15 this I told no, Ex, Ey, Hy, from that equation, which is a function of Ez and Hz. So along with this and the boundary conditions, we can find the other components of. So as I already mentioned, we are going to find the components of electric and magnetic field along the X and Y direction, okay, by using the equation 12.11, that is EZS. Along the wave direction, we have already found this. And similarly, we have found in the 15th set of equations, Ex, Ey, Hx, Hy. And along with these two sets and boundary conditions only, we are going to find first, determine the Ez component. Okay. So we are going to assume the boundary condition that at walls of the waveguide, okay, walls are actually perfect conductors. So in perfect conductor, tangential component of electric field must be continuous. What is the meaning of that? Tangential component means what? This wall, what is the tangential component? It is along the Z direction. So Ez is component, okay, it's 0 for the all the walls, okay, top bottom both side walls. Okay, so I am finding that boundary at y equal to 0, that is bottom wall. Similarly at y equal to b also the Ez is 0, and in the same way, if I take the right hand side wall, x is equal to 0, same at left hand side, x is equal to a. For all the cases at the boundary, Ez is 0. So we are going to apply that boundary condition in this particular equation 12th. So what we can find, if x, we are going to apply first the a and c condition. Okay, that is y equal to 0, x is equal to 0. At the origin, if I apply the boundary, we can see that cos 0 will come here, sin 0, cos 0, sin 0. So we know the value of cos 0, it is 1. Sin 0 is 0. So this entire term, okay, get vanishes. But I need to equate this particular equation to 0 because Ez is 0, right? So existing terms are a1 and a3 only because cos 0 is 1. These terms are neglected. So what is meaning, if Ez has to be 0 means a1 a3 has to be 0 obviously. So we are going to apply a1 a3 as 0 in this equation, and we are going to rewrite the 11th equation in this manner. Ez is nothing but, okay, what will come? A2 A4 sin kxx sin kyy into e power minus gamma z, where A2 A4 we just replace by other constant E0, that is the amplitude of the electric field. So if we apply the rest two condition, that is at x is equal to a and y equal to b, what happens? This equation that we got after substituting a1 a3 equal to 0 to this 18th equation, we know that a sin kx into a sin ky into b, everything is going to be 0, right? I'm going to separate the terms and write separately 0. Okay, when the sign value will be 0 if it is multiples of pi. So the m1 I am taking for kx a, it is equal to m pi, kyb as n pi. Some integers I am taking. So the m1 and integers values ranges from 1 to 3, where kx is nothing but, from this equation it is m pi by a, ky is nothing but n pi by b. So negative values we can't take it. Okay, and we are going to substitute these kx and ky in this 18th expression and rewrite Ez as E0 sine. For kx it is m pi x by a. Okay, similarly sine ky, instead of ky, n pi by by e power minus gamma z. We are going to find Ex, Ey, Hx, Hy by the known value of Ez by partially differentiating this particular expression with respect to x and y, okay, in all the things. So we already know that in transverse magnetic mode, Hz is 0. So I have just written out this the second component. So I will explain about the first component Exs, that is going to be the constant will remain same, and the differentiation of this sine term, okay, we get cosine function, and we have to multiply this constant before m pi by a, and the next term will be there as it is. In similar manner, we have to find the other components Ey, Hx and Hy, and now here the H is going to be, and c H square is going to be k square, kx square plus ky square, that is equal to m pi by a the whole square plus n pi by b the whole square. So these equations we already obtained, right? From the 16th and 21st equation, this equation kx ky I am substituting, 16 we already saw in the previous session. So now from these set of equation, that is equation 22, that E is as equation, we have only 5 terms, right, out of the 6 wave equations in rectangular waveguide for transverse magnetic mode. Since one field component is already 0, we have the 5 terms. Combining all these terms, we can note that we have the set of integers m and n. In all the equations, there are set of integers. So if we give different value for this set of integers, we get different field pattern or mode. That is called as TM M suffix mn mode. So here the integer m represents the number of half cycle variations in the x direction, and n represents the number of half cycle variations in the y direction. So we can also understand one more thing from these set of 5 equations, that so if m and both are equal to 0, or any one of the component, m is 0, n is there, or m is there, n is 0, if you could see here, if any one of the component or both components are 0, all the field components get vanishes. Why? Because if any of the component is 0, you can see here all are sign terms. Sign 0 is 0. Here also I can't take the n value as 0, okay, because entire term vanishes. In this expression m, I can't take 0. So in all the cases, I can't take these values as mode numbers, okay. It cannot be 0 always, okay. So TM11 is the lowest order mode of all the available modes in TM-MN mode. So from 16th equation, we know that head square is equal to gamma square plus k square, and that is again equal to kx square plus ky square. So we are going to substitute the value that we got for kx and ky, right, in the 16th equation, and find the propagation constant gamma. That is, what is gamma here? It is the root of head square minus k square. Whereas head square is nothing but m pi by a the whole square plus n pi by b the whole square, and this minus k square is there as it is, where k is known as omega into root of mu epsilon, right? So we generally know that gamma is nothing but alpha plus j beta. That is, propagation constant is the sum of attenuation and phase constant. So we have three possibilities, okay, depending on the value of k, or we can say the omega, and m and n values. Okay, these only will dictate the k value, m and n value. Depending on this, we have three different possibilities that we will see in the upcoming session. I hope you understood about the transverse magnetic mode in rectangular waveguide. We will continue in the next session. Thank you, everyone.